Hello everybody, welcome to my presentation about clustering persistent scatterer points based on a hybrid distance metric. My name is Philipp Schneider, I'm with the Institute for Photogrammetry at the University of Stuttgart. As a little motivation, I want to show you this. This is downtown Stuttgart, Germany, with the main station and the Institute for Photogrammetry right here. And this is the main station. What you see here are building footprints, and the color indicates the velocity of how these buildings were moving between 2016 and 2020. The velocities are measured with interferometric synthetic aperture radar, and I will explain more about this in a bit. The reason for these movements are getting clear when I show you the newly constructed train tunnels right here. Even though this 1 centimeter movement per year sounds very dangerous, but the majority of these buildings did not suffer from any damage. And my research is that I'm trying to find ways to separate harmless movements from dangerous movements and activities. And I do that by analyzing substructures of the building and the movement of these substructures. The overall goal of this work is the integration of PSI, which is the underlying synthetic aperture radar technique we have to talk about, into building information management systems and digital twins. And I do that by segmenting PSI points on buildings into substructures and assign them to building parts. And in previous work, we showed the plausibility of such clusters and compared them to ground measurements. And today I want to talk about a hybrid distance metric that helps to improve the quality of the PS clustering process. I will briefly explain the PSI principles so you understand where the data we are using here is coming from. And then I will explain our reverse geocoding approach that we use to transfer the labels into SAR geometry. And I will explain the distance metric we use in a nonlinear dimension reduction to cluster the PS points on the building. And finally, I will show some actual houses that suffer from minor damage from the tunnel construction and a web-based tool we developed to show the results on a much bigger building complex. So let's talk about persistent scatterer interferometry. It's a differential synthetic aperture radar technique. And we start with a stack of high-resolution SAR images. In this work we are using 132 images from the German satellite TerraSAR X. And the stack means that every 11 days when the satellite comes back to the same position, it takes an image. And in difference to normal camera images, a SAR image also contains the phase of the incoming signal. And by comparing the phase of each image in the stack relative to a master image, we can detect very fine movements. This works especially well for urban areas, since metal objects and buildings are good reflectors. But on vegetation and water, the phase decorrelates and we don't get measuring points. So the main product from this PSI analysis is a 3D point cloud with the 3D position of these points estimated, but most important, the deformation history for each point. So we get a measurement for deformation measurement for each of these images. Here we see a PS point cloud overlaid with a 3D city model. And what we can see here nicely is that the points appear on the roof and on the facades of building, but we don't get any signal in vegetation or here where this construction is going on. The interesting thing, like I said, for each point we get the deformation history over the time. So for each image in our stack we get the movement in millimeter accuracy. Since we want to investigate into single buildings, we use building footprints from OpenStreetMap to segment the PS point clouds into building instances. For this, we choose to use a reverse geocoding approach that firstly transfers the footprints into SAR geometry, and because we know the original SAR pixel for each PS point, we can use this to assign each point to a building without the ambiguity in the estimated UTM coordinates. To understand the reverse geocoding, we need a quick overview over the SAR imaging geometry. So each point in the scene is mapped on the distance range from the satellite. So this point is mapped here, this point is mapped here in the range from the satellite. And this leads to layover and foreshortening effects. So the building seems to fall towards the satellite because the rooftop is closer to the satellite than the base of the building. In the real world, this looks like this. So here in this point cloud, you see this rather high building, and this seems to fall here over the street. So it's actually the same building like here. In the SAR image, it falls over the street. To compensate these effects, geocoding, a process similar to orthophoto generation, is used. With the help of a precise digital surface model and the satellite's orbit parameter, a geocoded image in world coordinates can be produced. And we use a commercially available geocoding software to geocode. Instead of the SAR image, we geocode a lookup table. And we use a precise digital surface model and receive the lookup table in XY coordinates. And this later can be used to transfer the labels from the world coordinates into the master image's geometry. So in a wrap-up, we start with a digital surface model and the building footprints and create a map of the buildings in SAR coordinates. This map then can be used to label the PS point cloud without ambiguities. Now we have all PS points on a single building, and each PS point has its time series. And one can now treat these time series as points in a deformation space with one dimension per deformation date. So here I choose 3 dates, but in reality it's this mentioned 132. So on date 1, this point moved this and this far, and on day 2 they moved this and this far, and on day 3 they moved this and this far. And you already see clusters forming here. And the assumption is that these clusters show a correlated deformation behavior because they lay on the same rigid structure. So we have, for example, this blue cluster here, and the assumption is that it's on the same rigid structure, for example, the roof, or the red ones are all on the facade. And because of this rigid structure, they show a correlated deformation behavior. To describe the similarity of 2 points, we use a hybrid distance metric. Previous work has shown that 1 minus the sample correlation is a good metric for the similarity of 2 points' displacement histories. To also take into account the spatial relation, we use a normalized Euclidean distance. We combine those 2 distance metrics as follows. The lambda factor allows for to weight one or the other distance more, but in the following we fix it to 1. Clustering in these now 132 dimensions is quite unreliable and comes with various cursive dimensionality problems. Therefore, we use UMAP with the previous mentioned distance metric to embed these high dimensions into 2 dimensions while preserving local neighborhoods. In these 2 dimensions, we can analyze the core distance graph to filter out points that are not part of a cluster. Afterwards, we can use dbScan to cluster the remaining points. Here we also use the core distance to automatically estimate the hyperparameter epsilon. We can now look at each cluster's deformation history and calculate the centroid in deformation space. We use the 1 minus sample correlation distance to filter out points that are too far from this movement. This helps the later results to be more clean. So this leads to the results. The building we want to look at knowingly suffered from damage in May 2019, when cracks occurred on the facade and inside the building. Those are clusters we extracted from the PS points on this house. For each cluster, we also get the deformation history for all the points here in black, and can calculate the mean velocity of the cluster, which is here the color of the cluster. We can also look at the spatial distribution of the points on the building, and remember that the positional accuracy of the points is in order of meters, so this is the position of the PS points on the building. And so let's look a little bit at the time series and what happened there. We see this rupture here in May 2019, and some parts of the building are moving upwards, like this green part here, which indicates this part, and some parts are moving downwards, like the purple one over here. And sadly, the responsible tunnel construction companies are very silent if you ask them about the cause of such movements. We also developed a web-based tool that helps to visualize the extracted clusters on a second, much bigger building. And I encourage you all to explore that yourself. You can visit this website by either scanning this link or typing this into your desktop browser. So on this website, you can see the 3D representation of another building complex, and you can move freely around, zoom in, zoom out. And on the right hand side, you see the deformation histories of all the extracted clusters in this complex. By clicking on the cluster, you can highlight where the position of the cluster is. You can turn individual clusters on and off. You can also hide and show the point cloud to get a more unincluded view where the position of these clusters are. Additionally, you also find the previously presented smaller building here. Works the same. You can turn on the clusters and investigate in the exact position of each of the points and the clusters relative to each other. And the reason why we felt the need of a platform like this is that it's very hard to show civil engineers and decision makers our findings. So we thought this 3D presentation seems a good way to get in touch with them. So this brings us to the end of my video. We have shown that a nonlinear dimension reduction based on a hybrid distance metric followed by a clustering can segment PS point clouds into plausible substructures, which represent rigid parts of a building, and therefore let us investigate into movement of individual parts. Future work and actual work in progress is to link the so found structures to a building information modeling system. And also very interesting is the analysis of these clusters relative to each other to come up with a citywide per building risk assignment. Thank you very much.